Chapter 7 Scheduling Introduction. By now, low-level mechanisms of running processes, for example context switching, should be clear. If you are not, go back to the chapter or two and read the description of how they stop work again. However, we have yet to understand the high-level policies that our OSU employs. We will not do just that, presenting a series of scheduling policies, sometimes called sprints, that various smart and hard-working people have developed over the years. The origin of the scheduling, in fact, predate computer systems. Early approaches were taken from the field of operating management and applied to the computers. This reality should be no surprise. Assembly lines of many other human endeavors also require scheduling, and many of the same concepts exist therein, uh, including a laser-like desire for the efficiency. That's our problem. The crowd, how to develop a scheduling policy, how we should develop a basic framed for thinking about the scheduling policy. What are the key assumptions? What metrics are important? What basic approaches have been used for earliest computer systems? Section 7.1 Workload Assumptions. Before getting into range of possible policy, let us first make a number of simplifying assumptions about processes during the system, something sometimes collectively called the workload. Determined workload is a critical part of the building policies. And the more you know about the workload, the more fine-tuned your policy can be. The workload assumptions we make here are mostly unrealistic, but that is all right for now because we will list them as we go and eventually develop what will develop differ to as the multiples. A fully operational scheduling discipline. We will make the following assumption about the processes, sometimes called jobs, that are running in the system. 1. Each job runs for the same amount of time. 2. All jobs arrive at the same time. 3. Once started, each job runs to the completion. 4. All jobs only use CPU, that is, they perform no I/O. 5. The runtime of each job is known. We said many of these assumptions were realistic, but not just as some animals are more equal than others in the Orwell's Animal Farm 045. Some assumptions are more unrealistic than others in this chapter. In particular, we might bother you that the runtime of each job is known. This would make the scheduler omniscient, which although it would be great, probably is not likely to happen anytime soon. Section 7.2 Scheduling Metrics. Beyond making workload assumptions, we also need one more thing to enable us to compare different scheduling policies. A scheduling metric. A metric is something that we use to measure something, and there are a number of different metrics that make sense in scheduling. For now, however, let us simplify our life by simply having a single metric, turnaround time. The turnaround time of a job is defined as the time at which the job completes minus the time at which the job arrives in the system. More formal, the turnaround time. The turnaround equals T completion minus T arrival. Because we have the assumption that all jobs arrives at the same time, for now T arrival equal 0 and hence T around equal T completion. This fact will change as we left the around mentioned assumption. You should note that the runtime is a performance metric, which will be our primary focus this chapter. Another metric of interest is the fairness, as measured, for example, by James Fairness Index. Performance may optimize performance, but at the cost of preventing a few jobs from running, thus decreasing fairness. This conundrum shows us that isn't always perfect. 7.3 First input, first out. First in, first out. FIFO. The most basic algorithm we can implement is known as first in, first out FIFO scheduling, or sometimes first come, first serve FCFS. FIFO is a number of positive properties. It's clear, simple, and thus easy to implement, and given our assumption, it works pretty well. Let's do a quick example together. Imagine three jobs arrived in the system A, B, and C at roughly the same time. The arrival is 0 because the FIFO has to put some job first. Let's assume that while they arrived simultaneously, arrived just as a hair before the B, which arrived just a hair before the C. Assume also that each job runs for 10 seconds. What will the average turnaround time to be for these jobs? Figure 7.1 FIFO simple example. From figure 7.1, you consider that A finished at 10, B at 20, and C at 30. Thus, the average turnaround time for the three jobs is simply 10 plus 20 plus 30 over 3 equals 20. Computing turnaround time is as easy as that. So now let's relax on our assumptions. In particular, let's relax assumption 1, and thus no longer assumption that is the stop. Each job runs for the same amount of time. How does FIFO perform now? What kind of workload could you construct to make FIFO perform poorly? Think about this before reading on keeping thinking and got it. Presumably you figured this out by now, but just in case, let's do an example to show how jobs different lengths can lead to trouble for FIFO scheduling. In particular, let's again assume the three jobs A, B, and C, but this time A runs for 10 seconds while B and C run for 10 each. Figure 7.2 why FIFO is not that great. As you can see in the figure 7.2, job A runs FIFO for the first full 100 seconds before B or C even get a chance to run. Thus, the average turnaround time for the system is high, a painful 110 seconds. 100 plus 110 plus 120 over 3 equals 110. This problem generally refers as the convoy effect, where the number of the relatively short potential consumers of resources get queued behind the heavyweight resource consumer. This scheduling scenarios might behind you a single line at a grocery store, and what you feel like when you see the person in front of you, the three carts full of provision and checkbook out, it's gonna be a while. So what we should do? How can we develop a better algorithm to deal with our new reality of jobs that run for a different amount of the time? Think about it first, and then read on. Tip: the principle of SJF. Shortest job first present a general scheduling principle that can be applied to any system where the perceived turnaround time per customers or in our case a job matters. Think of the line you have waited in. If the establishment questions cares about customer satisfaction, it's likely they have taken SJF into account. For example, the grocery stores commonly have 10 items of less line to ensure that a shopper with only few things to purchase don't get stuck behind the family preparing for some upcoming nuclear winter. So 7.4, the shortest job first to SJF. It turns out a very simple approach solved this problem. In fact, an idea stolen from the operation researchers and applied to a scheduling jobs in a computer system. This new scheduler's discipline is to the short step first, SJF. And the name should be easy to remember because it describes the policy quite completely. It learns the short step first and the next shortest and so on. Let's take our example of both the SJF as our current scheduling policy. Figure 3.7.3 shows the result of running A and B, A, B, and C. Hopefully, the diagram makes clear why SJF performs much better with regard to the average turnaround time simply by running B and C before A. SJF registers average turnaround from the 1 and 10 second to 50. 10 plus 20 plus 1 and 20 over 3 equals 50, more than a factor of 2 improvement. Aside preemptive schedulers, in older days of the batch computing, a number of non-preemptive scheduling were developed. Such a system would run each literal completion before considering whether to run a new job. Virtually all modern schedulers are preemptive and quite willing to stop one process from running in order to run another. This implies that the schedule employed mechanism we learned about previously. In particular, the scheduler can perform a context switching, stopping the learning process temporarily and resuming or starting another. In fact, given our assumptions about the jobs or driving at the same time, we could prove the SJF is indeed an optimal scheduling algorithm. However, you are in a system class, not theory or operation research. The proof are allowed. Thus, we arrived upon a good approach to scheduling with SJF, but our assumptions are still fairly unrealistic. Let's relax another. In particular, we can target assumption 2 and now assume that we can apply it at any time instead of all of us. What problems does this lead to? Another pose to think. Are you thinking? Come on, you can do it. You here we can illustrate the problem again with the example. This time, assume A arrives at t equals 0 and needs to run for 100 seconds, whereas B and C arrives at t equals 10 and each need to run for 10 seconds. With fewer SJF, we would get the schedule seen in figure 7.4. 7.4 is SJF with the later arrivals from B and C. As you can see from the figure, even though the B and C are arrived shortly after A, they still are forced to wait until A has completed and thus offered from the same combo problem. Average turnaround time for the three jobs is 103.33 seconds. 100 plus 110 minus 10 plus 120 minus 10 over 3. So what can be the schedule to do? 7.5 is shortest time to completion first, STCF. To address the concept, we need to relax assumption 3, that jobs must to accomplish time. So let's do that. We also need some machinery within the scheduler itself, as you might have guessed, given our previous discussion about timer interrupt and context switching. The scheduler can certainly do something else when B and C arrive. It can preempt two jobs A and decide to run another job, perhaps continue A later. As our definition is non-preemptive scheduler, and thus suffers from problems described above. Fortunately, there is a scheduler which does exactly that, as a preemptive to SJF, known as shortest time to completion first, STCF, preemptive shortest job first, PSJF scheduler. Anytime a new job enters the system, the STCF schedule determines which of the remaining jobs, including the jobs that has the latest time left, and is scheduled on that. Thus, in our system, STCF would preempt A and run B and C and to completion. Only when they are finished would A remaining time to be scheduled. Figure 7.5 shows an example. The result and the much improved average turnaround time, 50 seconds, 120 minus 0 plus 20 minus 10 plus 30 minus 10 is over 3. And as before, given our new assumptions, STCF is probably optimal, given that SJF is optimal if all jobs arrive at the same time. You should probably be able to see the institution behind the optimality of the STCF. 7.6 A new metric, response time. Thus, if we knew the job strength, that the job only used the CPU, and our only metric was turnaround time, STCF would be a great policy. In fact, a number of early patch computing systems, these types of scheduling algorithms made some sense. However, the introduction of time-sharing machines changed all that. Now the users would sit at a terminal and demand interactive performance from system as well, and thus a new metric was born, response time. And we define response time as the from the what the when the arrives in a system to the first time it is scheduled. More formally, t response equal to the equals t first to run minus t arrival. Figure 7.6 SJF again, better for response time. Figure 7.5 round robin the good for response time. The for example, if we had a schedule from figure 7.5 with arriving time at time 0 and B and C at time 10, the response time of each job is as follows: 0 for job A, 0 for B, and 10 for C, average 3.33. As you might be thinking, STCF and related discipline are not the particular good for the response time if the three jobs arrive at the same time. For example, the third job has to wait for the previous two jobs to run in their entirety before being scheduled once just one. While greater for turnaround time, this approach is quite bad for response time and interactivity. Indeed, imagine sitting at a terminal typing and having to wait 10 seconds to see a response from system just because some other job got scheduled in front of yours. Not too pleasant. Thus, we are left with another problem. How can you build a scheduler that is sensitive to response time? 7.7 Round Robin. To solve this problem, we will introduce a new scheduling algorithm classically referred to as round robin or arm scheduling. The basic idea is simple. Instead of running jobs in completion, R runs a job to the time slice, sometimes called the scheduling quantum, and then switch to the next job in the run queue. It repeatedly does so the two jobs are finished. For this reason, R is often called the time slicing. But the length of the time slice must be a multiple of a timer interrupt period, thus it times every 10 seconds at a time, will accrue to 120 only other multiple over 10 microseconds. To understand the RR in more detail, let's look at an example. Assume three jobs A, B, and C arrive at the same time in the system, and that they wish to run for 5 seconds. On a stage schedule runs each job to completion before running another. In contrast, RR with a time slice of 1 second would cycle slice just quickly, figure 7.7. So tip, amortization can reduce the cost. The general technique of amortization is commonly used in systems where there are fixed costs to some operation. By incurring that cost less often, for example by performing operation fewer times, the total cost of the system is reduced. For example, if the time slice is set to 10 nanoseconds and the core text switch cost is 1 nanosecond, roughly 10% of time is spent the context switching is then a thread. That's the best thing. If we wanna amortize this code, we can increase the time slice. For example, is to in this case 100 microsec in this millisec. In this case, less than 1% of the time is spent context switching, and thus the cost of time slicing has been amortized. The average response time of RR is 0 plus 1 plus 2 over 3 equals 1. For SJF, average response time is 0 plus 5 plus 10 over 3 equals 3. So as you can see, the length of the time slice is critical for RR. The shorter it is, the better the performance for RR under the less response time metric. However, making the time slice too short is problematic. Suddenly, the cost of the context switching will dominate the overall performance. Thus, deciding the length of the time slice represents trade-off the system to be designers making it enough to amortize the cost of switching without making it so long the system is no longer responsive. Note that the cost of the context switching doesn't arise solely from the OS actions, saving and restoring a few registers. When a program learns to build up a great deal of state in the CPU caches, TL bits, and branch periodically, and other on-chip hardware, switching to another job making this superior flash to a state resolution can state relevant to a currently the running jobs to be brought in, and which may exact a noticeable performance on cost. RR, round robin with a reasonable time slice, is thus our excellent scheduler. After response time is our only metric. But what about our older friend turnaround time times over 5 seconds? Live at the same time as our scheduler with a long and 1 second slice. We can see the principle We can see from the picture above that A finished at 13, B at 14, and C at 15, for average of 14. Pretty well, awful. It's not surprising that the RR is indeed one of the worst policies if the turnaround time is our metric. Intuitively, this should make sense. What the RR is doing is straightening out of each job as long as it can by only learning each job for a short bit before moving to the next, because the turnaround time only cares about when jobs finish. RR is nearly pessimal, even worse than a simple FIFO in many cases. More generally, any policy such as RR is that fair. That is, evenly divide the CPU among the active processor's time scale, small time scale, will perform poorly on metrics such as turnaround time. And this is an inherent trade-off. If we are willing to infer, you consider shorter jobs to completion, but at the cost of response time, if you instead of volume fairness. And it is an inherent trade-off. If you are willing to unfair, you can restrict shorter jobs to the completion, but at a cost of response time. If instead of valuable time, response time is lowering, but the cost of turnaround time, this type of trade-off is commonly in a system. You can't have your take it is eat and your take and eat it too. The overlap enables a higher utilization. When possible, overlap operation to maximize the utilization of the systems. Overlap is useful in many different domains, including when the performing disk I/O or sending message to remote machine. In either case, starting the operation and then switching to other work is a good idea and improve the overall utilization and efficiency of a system. We developed two types of schedulers. The first type, SJF STCF, optimizes turnaround time, but it is bad for response time. The second type, other optimizes response time, but is bad for the turnaround time. And we still have to assume that we need to be relaxed. Assumptions for the type do not have their jobs do no I/O. Assumption 5 that the runtime of each is unknown. Let's tackle these assumptions next. The 7.8 incorporating the I/O. First, we will relax the assumption 4. Of course, all programs perform I/O. Imagine a program that didn't take any input. It would produce the same output each time. Imagine one instead of output. It is provisional 3 falling at 4 last with no one see it. It doesn't matter when and when. A short schedule clearly has a learning job want to be using the CPU during the I/O. It's blocked waiting for I/O completion. If the I/O is sent to the hard disk drive, the process might be blocked for a few milliseconds or longer. Depending on the current I/O load of drive, thus the scheduling should probably schedule another job GPU at the time. The scheduler also has to make a decision when the I/O complete, when the occurs, when interrupt is raised, and OS learns and moves the process that issued to the I/O from the blocked back to the ready state. Of course, it could even decide to run at that point. We should the OS treat each time. To understand this better, let us assume we have two jobs, A and B, and which needs 50 millisecond of the millisecond CPU, 50 second of the milli of CPU time. However, there is one obvious difference. Along for 10 millisecond and then an issue to an I/O request. Assume here is I/O take 1 millisecond, whereas B simply uses the CPU for 50 millisecond and perform no I/O. The scheduler runs A first and B after figure 7.8. Assume we are trying to build a STCF scheduler. How should such a scheduler account for the fact A is broken up into 5-10 millisecond subjobs? Figure 7.9 overlap allows better use of the resources. Figure 7.8 poor use of the resources. Where B that risk singular 50 millisecond CPU demands clearly just running one job and then other without considering how to take I/O into account to make little sense. A common approach is to treat each 10 millisecond subjob of A as an independent job. Thus, when the system starts, each choice is whether to schedule 10 millisecond A or 50 millisecond B. With the STCF, the choice is clear. Choose the shorter one. In this case, A. Then the first subjob of A has completed, only B is left, and B begins learning. Then a new subjob for submitted, and let's preempt the B and runs for 10 milliseconds. Doing so allows for overlap with the CPU being used by the one process while waiting for the I/O of other process to complete. The system is thus better utilized. See figure 7.9. And thus we see how scheduler might incorporate I/O by treating each CPU burst as a job. The scheduler makes sure processes that are interactive get run frequently, while those interactive jobs are performing the I/O, and other CPU-intensive jobs run, thus better utilizing the processor. 7.9 No more clutter. With a basic approach to I/O in playlist, we come to our final assumption that the scheduler knows the length of each job. As we said before, that is likely the worst assumption we could make. In fact, a general purpose OS like the ones we care about, the OS usually knows very little about the length of each job. Thus, how can we build an approach that behaves like SDF without such prior knowledge? Further, now we can incorporate some of the ideas have been seen with the RR scheduler so that response time is also quite good. 7.10 Summary. We have introduced the basic ideas behind scheduling and developed two families of approaches. The first learned short job remaining and thus optimizes turnaround time. The second alternative because of the jobs and optimized response time, both are bad and the other is good. Or alas, the inherent trade-off common in system. We have also seen how we might incorporate I/O into the picture, but have still not solved the problem of the fundamental inability of the OS to see in the future. Shortly, we will see how overcome this problem by building a scheduler that uses the recent past to predict the future. This scheduler is known as a multi-level feedback queue, and then is topic of next chapter. And references and homework. Thank you for your time. See you next time.